Go, 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 go! Yeah! Home run! Oh my gosh, oh my gosh. Hey guys. Wait, okay, hang on 1 second. Here it comes the... Alright. Well, speaking of waves, if you guys are here, that can only mean one thing, that it is time for...
a physics break.
In class lately, we have been talking about waves. Now, in particular, we spent a physics break a few weeks ago talking about sound waves and the speed of sound. But there are other kinds of waves, like the wave we just did at the ballpark, and other waves as well, like light. And we have been talking a lot about light. In our last physics break, we talked about how light changes with the distance, and in class, we've been talking about how light travels and what light does as it travels. And today, we're going to be talking about light, and in particular, we will be measuring the speed of light. You heard that right. We're measuring the speed of light in our very own homes with no fancy equipment at all, just a microwave. And we can use our microwave because microwaves, just like light waves, are part of the electromagnetic spectrum. Now, all waves in the electromagnetic spectrum, be them ultraviolet, microwave, or light, travel at the same speed. So if we find out the speed of a microwave, we found out the speed of light. Pretty cool, huh? The way we're going to do this all relies on how waves travel and the properties of those waves. The way your microwave works is it creates two waves that travel in opposite directions and create what's called a standing wave. Now, a standing wave is kind of weird, so here's a GIF showing you how it looks. What standing waves do is essentially oscillate up and down because the two waves interfere, creating either constructive interference, causing a more intense wave, or destructive interference, causing a less intense wave. Nodes and peaks. Now, the peaks and the troughs, the part of the wave that's oscillating up and down, that oscillation causes things to heat up. In this case, it causes food to heat up. Those nodes, those points in the middle, the red points that aren't moving, those cause our food to stay cold. This is why microwaves rotate, why they have that turntable in the middle that spins. Without the spin, you're only heating up certain parts of your food. With the spin, you kind of get more coverage and your food heats more evenly. So what we're going to do today is remove the spin because standing waves have these hot spots and cold spots that are dependent on the wave length. The longer the wave, the bigger distance between hot spots. We can measure our wavelength and use that to find the speed of light because it's a very, very important relationship that the wavelength of light, something we can measure, let's say in meters, times the frequency of the wave, something we measure, say, in 1/seconds, can be multiplied together to get, you guessed it, a speed. A meter thing and a 1/second thing multiplied together to give us a meters per second thing, or a speed. In this case, the speed of microwaves, and therefore the speed of light. Welcome to my kitchen, PhysCalc. So to do this experiment, you will also need to be in your kitchen because we need the microwave. And in addition to the microwave, there are a couple of other things you'll need. A microwave-safe dish. I'm using this glass pie plate, and the bigger the dish, the better. So something kind of roughly this size, a good idea. A plate would work. Anything microwave-safe that can hold stuff in it, you're gonna want to use. So I've got my microwave-safe pie dish, and I've got something to melt. I'm going to use this giant jar of chocolate chips. I'll just sprinkle some into my pie plate. But this experiment can also be successfully done with egg whites or marshmallows. And I encourage you guys to branch out and try melting different things to see what gives you the most accurate results. Now, do not waste food. I'm going to be taking my melted chocolate chips when this experiment's over and turning them into a chocolate chip cheesecake. So don't waste food. Be aware that whatever you're melting should then be used, and make sure you're using something efficient so that you can then not waste it when this experiment is over. Because we love science, but not enough to waste food. So now that my experiment materials are gathered, my melting thing and my thing to melt in, what I'm going to do now is prep my microwave for this experiment, because in the modern era, we have done a great job of making microwaves very good at cooking food. But we don't want to cook food in a good way. We want to cook food in a scientific way. So microwaves have these turntables that spin, allow your food to get nice and evenly warmed, but we're gonna cut those out. Some microwaves have a setting that says turntable on off. My parents' microwave, for example, has one of these. It's very effective, super efficient. So if there's a button on the front of your microwave that tells you can turn off your turntable, just do that, nice and easy. My microwave doesn't have one of those though, so I'll go ahead and split screen and show you what I'm about to do. I'm gonna open up my microwave. I'm going to remove the plate from the inside. Now, the turntable plate is pretty easy to remove. It just pops right off because inside my microwave is this rotating little sort of circle. Now, in my case, we're gonna wanna cover it with something, and it turns out that the turntable is the perfect size to just flip over and put right back on top. Doing that, I am no longer having my little glass tines hit the rotating motor. So at this point, even though the motor still spins, it's not going to be hitting the plate and nothing will rotate. And we can do a quick test. I'll just close my microwave, give us like a 5-second cook. Look in, and my plate's not turning. So I'm good to go. So you just want to make sure that when you microwave your food, it's not going to spin. Cover that turntable and make sure that nothing's going to happen. If you can't cover it with your own sort of like turntable glass piece, maybe take something like this, flip it upside down, put it over that motor. You're gonna have to get a little creative. Everyone's microwave is different, but I'm sure you guys can figure out a way to safely get that turntable out of the equation. Now that my turntable is taken care of and I have a setup that is conducive to my experiment, I need to get my experiment ready in my pie plate. So I'm gonna take my pie tin, and I'm just gonna give it a full layer of chocolate chips. And yes, I do have a giant jar of chocolate chips just hanging out in my kitchen. That's the kind of person that I am. Do with that what you will. So I'm just gonna get my chocolate chips in my pie plate. So we got there, that's a pretty good layer. And we want to be, like, we wanna have good coverage. So I don't wanna be, I wanna make sure they're really in there so I can really see the melty parts. Let's sort of level this out here. Beautiful. Look at that. Full coverage. I'm not going to be able to show you without messing it up, but there's a nice layer of chocolate chips on my pie plate. Now I'm just going to want to put it in the microwave. Make sure my turntable is still good to go. And this is the tricky part, because even though we're doing a science experiment, there's no exact science to how long you should leave the chocolate or marshmallows or whatever in the microwave. Our goal is to see where the oscillations and the waves we just talked about are and are not. So we want some of the chocolate to be melted and some of the chocolate chips to still be cold. So my goal is to cook it for long enough that some parts are melty and some parts are not. Now, the tricky thing is, if I take the plate out, it is going to be really hard for me to put it back in at the exact same spot. So my goal is to do this without ever removing the pie plate. I'm lucky, I'm tall, I might be able to see in it, but we'll see how it goes. I'm gonna start with 25 seconds and hope for the best. So I'll see you guys in 25 seconds. Okay, 25 seconds are up. I am in fact tall enough to see the actual plate, which is great. I see no melty parts. Let's try 45 seconds this time. We don't want to burn it though. I don't want any like smoking, burning microwaves. I don't want anyone's parents calling me complaining about you burning down kitchens. So be careful, be modest, a little bit at a time. Let's try 45 seconds. Okay, I feel like similar to a watch pot never boils, watch chocolate probably never melts, so I'm gonna just like, I'm gonna not watch it. Okay, maybe I'll watch it a little bit. Oh, I'm seeing some melting. It's getting melty. Oh yes, this is going much better this time. All right, melty chocolate take 2. Okay. Okay, I'm nervous to take it out because I can see parts are melty. I think we're gonna do it. I think we're gonna do it and see what happens. It's out of the microwave. Oh, it's so hot. It's so hot. Please be careful. I'm also gonna fix my microwave so I don't forget. We're just gonna flip this guy back over. Okay.
Microwave is back to normal. Science experiment is done. I'm going to grab the camera and show you guys what this looks like, and we'll finish up the experiment because our microwave portion is hopefully over. All right, so you can see here, some parts look meltier than others. You can see we've got some nice sort of unmelted chocolate chips and then some melty chocolate chips. And this is the difference in distance between the high oscillation point of my waves. This is where it was oscillating, and the dead zones, my nodes. So I've got some good stuff here. Now my goal is to measure between the non-melted parts. So what I'll do is I'll take a picture and I'll sort of map out what I'm measuring, and then I'll measure it IRL as well to give you guys a sense of what you want to do. But when I measure the distance between, for example, this cold spot and this cold spot, so the distance between them, luckily chocolate gets all shiny, so it's easy to see. Get a couple of them because we'll average them for the real distance and take some measurements. So I'm going to average about 3 or 4 distances as I can find them to figure out the distance between roughly the centers of my cold spots. And again, here's what I'm doing. Cold spot, the distance between them, that's what I want to know. All right, so my measurements are done, and I got there about 2.5 inches between cold spots on my dish of chocolate chips. Now, I just used my trusty pasta measuring ruler to find this out, measured about 3 spots, and for each of them got around 2.5 inches, so that's the number I'll be using there. The last thing we need to find the speed of light is to know the frequency of our microwaves. Now, there are 2 options here. The first is to find the precise frequency at which your microwave operates. Different microwaves are built differently, but many of them have stickers on the front and back. So there's a nice sticker here on mine that gives me lots of good information, but not the frequency, unfortunately. I read that lots of microwaves have stickers on the back of them that might have the frequency, so if your microwave's not built in like mine is, feel free to flip it around and see if you can find it. But this is not going anywhere. It's built in, I can't see behind it, and I rent an apartment, this is not my purchased microwave, and I can't seem to find the manual for it either. So in the absence of being able to find an exact value, no thanks to my microwave, I will use the general microwave radiation range that most commercial microwaves in the US have, which is about 2,450 megahertz. So if you can't find a sticker that has some number of hertz on it, you can assume it's about 2,450 megahertz, the way I will be assuming this for mine. So armed with these 2 pieces of information, that there are roughly 2.5 inches between cold spots, and that my microwave operates at around 2,450 megahertz, I am now ready to take you all to the virtual whiteboard to wrap up our calculation and tell you guys exactly how to use this information to find the speed of light. See you at the virtual whiteboard.
Welcome to the virtual whiteboard. I have here a standing wave, and we talked a lot about standing waves in the beginning of this video, and in particular, we talked about how the nodes, these middle parts, correspond to my cold spots in my microwave, and I measured during my experiment the distance between them. We'll call it delta x. Now, the distance between them is useful, but not on its own, because the measurement we want is a wavelength, and a wavelength is measured from both a trough and a peak. So I need both a trough and a peak to make my wavelength, meaning my wavelength, known as lambda, is actually equal to 2 times my distance. It is 2 delta x's back to back. So in my case, I measured delta x as 2.5 inches, meaning my lambda would be 5 inches. The last thing I need to know about my wavelength is that it needs to be measured in meters. If it's not in meters, my calculation won't work out quite right. Now that I have my wavelength, I need my frequency, or F. And my frequency, as we said, is 2,450 megahertz. Now, that's good and all. It's my traditional microwave frequency, but I need my frequency to be in hertz, because hertz is equal to 1 over seconds. Once I have those 2 values, my calculation is as simple as V equals lambda times F to get my final velocity. In my case, I got about 311 million meters per second, which is not too far off from the real value of 300 million meters per second. Not too bad at all.
And there you have it, measuring the speed of light with nothing but your microwave and a little bit of light. The real speed of light is about 300 million meters per second. How close did you get? All right, guys, that's it for this physics break. I will see you next time. Until then, PhysCalc.